The chemistry club is having this health session for all the classes. The health session for this class, as you can see, is at 5 p.m. on Thursdays. CC, I'm not sure what building that is. Campus Center, thank you. Campus Center to a PC. Yeah, originally this was going to be planned for the Learning Emporium. However, you'd be interested to know that in this day and age, somebody was worried about, are you ready for this? Liability. Because, yes, oh my God. Because it might end after 7:30, and you know, if one of you should trip and fall on your way to the parking lot, you know, someone might be liable. So that's why they're having it in the campus center. This is a sad commentary on you know, on how we do things around here, but I was not part of that decision, just to let you know. Okay, so I had a few questions about what's covered on the exam. Those of you who took 272 from me last semester know that the rule of thumb is that we cover material up to 1 week before the date of the finals. That would have been Wednesday of last week. So just to spell it out one more time, we're going to cover chapters 12, 13, 16, and just that little bit of chapter 17 that we did on Wednesday of last week, okay? So mainly it's going to be spectroscopy and electrophilic aromatic substitution. So let's pick up, excuse me, let's pick up where we left off last time. So last time we ended the discussion with just introduction to oxidative metabolism of xenobiotics. I said that your livers have a series of these enzymes called cytochromes, and that what these do is they recognize things that are not part of your body's normal, it's not stuff you eat. And these things get oxidized to make them water soluble so they can be excreted typically through your kidneys. And so the way this works is as follows. It's kind of an interesting mechanism. You have a protein, and the proteins vary, by the way, there's lots of these. But all of them have at their active site a porphyrin iron complex. So the porphyrin you're going to see in your book, it's got nitrogens at the four corners of this square. The nitrogens form bonds to the iron. Now the bonds that the nitrogens form to the iron are not the same. Two belong to one category, two belong to a different category. How organic compounds bond to metals is something we're going to talk about in the next chapter. So there's also a sulfur from a cysteine bonded to the iron, and then the iron is bonded to oxygen. So if you count up electrons, something again we're going to learn how to do next chapter, this is iron in its +5 oxidation state. Now, you know that iron has two normal oxidation states, iron 2, ferrocyan, and iron 3, ferric iron. We saw ferric iron as part of what? Ferric chloride, a strong Lewis acid catalyst for electrophilic aromatic substitution. So this is even higher in oxidation state. And so that tells you that this iron is probably pretty good, you know, that this species is going to be a pretty good oxidant. In fact, it is. And this is what it does. It takes an arbitrary CH, not an OH, but a CH, and it oxidizes it to an alcohol. Now, that is a really tough thing to do. And synthetic organic chemists would really love to have a toolbox where you could take any arbitrary molecule and say, aha, you know, I want this particular carbon to pull off a hydrogen atom and stick on a hydroxy radical, or hydroxy group. But in fact, you can't do that. And that's kind of too bad. Now, the other thing that is remarkable about the cytochromes is that they don't necessarily react with organic molecules at the site of highest reactivity. So let me indicate, we're going to talk about ibuprofen in a minute. Ibuprofen, as you probably know, is a very nice drug for aches and pains. And it looks like this. This is the structure of ibuprofen, Motrin. And now, the prediction you would make is that if we're going to form radicals on ibuprofen, that the most stable radical should be the one that's formed first. And you already know that benzylic radicals have a special stability associated with them. And in fact, we have two benzylic sites here. We have one benzylic site here and one benzylic site there. Those two sites are not the same. In fact, this is going to be the most reactive one, not only because it's tertiary, but because if you form a radical here, it is resonance stabilized by the carbonyl group of that carboxylic acid. So this will be the most stable radical. This will be the second most. And then the third most will be this tertiary one, which is not benzylic and not resonance stabilized. So if you're looking at the oxidation of ibuprofen, not by cytochrome, but just in the lab, your prediction probably would be that, well, probably get reaction here and then maybe reaction there. In fact, with the cytochromes, that's not what it's seen. With the cytochromes, it turns out that the site of reactivity is the tertiary position, which we've discussed, and also the primary one, but not benzylic. These are the major metabolites that your body produces when you take an ibuprofen pill. And so the question you might ask is, well, what's going on here? Do chemical rules not apply for enzymes? The answer is no, they do apply, but there's something else going on. What's going on is proximity. So here's the way you want to think about it. So you have this ibuprofen molecule. It comes into contact with an enzyme. And the enzyme has a fairly complicated three-dimensional structure, and the business end of it, this piece, is embedded in some kind of a pocket. Now, depending on the size and dimensions of that pocket, ibuprofen may not be able to fit in with this end. And so it may be only this end that can fit into that pocket. Therefore, oxidation can't take place at the chemically most reactive site. It can only take place at the site where it comes into contact with that iron +5. And so this is an effect that you can see with enzymes again and again. And so it's not that the rules don't apply, it's just there's a different rule that's superimposed, and that is driven by the proximity. So the enzyme's active site is where the molecule has to approach, and it's not always going to be the chemically most reactive site that gets attacked by the enzyme. So how does it work? Okay, so here's your cytochrome with the active oxidant. And if I draw a resonance structure here, I can draw a diradical. In fact, this is probably a little bit closer to the truth than that. And so this radical, this oxygen radical, can do a radical reaction where one electron is shared from the radical to this hydrogen, and one electron from the CH covalent sigma bond. So you form an OH, and that leaves behind a radical, a carbon radical, tertiary one. And so now what happens is that you get radical cleavage of this iron-oxygen bond. So another electron comes and sits on the iron. One of these electrons and the electron from here form an OH bond. And so in essence, this iron, which goes from +5 to +3, has done a 2-electron oxidation on that unactivated carbon. And so now your enzyme has a reduced form of iron. This is no good for oxidizing anything. And so in order for this now to be used again, there are a number of enzymatic steps that will oxidize the iron back up to iron +5. And so the metabolism does require quite a bit of energy from your body, right? So your body has to do quite a lot to generate the cytochrome P450 and then keep it in the right oxidation state for it to keep doing its job. Now, one thing to recognize, or a couple of things I want to say. First of all, this is not a radical chain mechanism, okay? So it's not as if you form a radical and that radical goes off and does stuff. This is not a chain reaction. This is two radicals combining. If it looks like anything, it looks like what? It looks like a termination step. And so this is called a rebound mechanism, and but it really looks like a termination. I mentioned something about your body having to expend a fair amount of energy for the metabolizing. And so when people develop drugs, they talk about metabolic load. Okay, so for example, when we talked way back when we talked about optical activity and stereochemistry, I said that your body typically will make use of only one enantiomer of a chiral drug. That's true for ibuprofen too, by the way. And so the other enantiomer is at best innocuous, or it may have a bad property. But even when it's innocuous, it has to be metabolized to be excreted. And so that requires your body to spend a lot of energy, as you just saw, to metabolize it, which is the metabolic load. So bottom line, you prefer to have single enantiomer drugs because they're more efficacious. They don't require that increase in metabolism. Now, if you know what the oxidative pathways are for metabolism of a drug, then there's a little trick you can play, as it turns out, and that is you can substitute the sites at which oxidation takes place. You can substitute the hydrogen for a deuterium. So this turns out to be D9 because it has 9 deuteria, as I've colored in here. Venlafaxine. That's just the trade name for an antidepressant drug. This is a central nervous system drug. And it turns out that oxidation takes place at the N-methyls and at the O-methyl. Those are the preferred sites for cytochrome oxidation. So what people have done is they've deuterated all those sites. So you just have the deuterated compound. Now, why does this work? Well, it works because you slow down the metabolism through an isotope effect. Remember that something we talked about, again, last semester, kinetic isotope effect. And so if in the rate-determining step we are breaking the bond to a deuterium, which is a stronger bond than to a hydrogen, then that particular step will be slowed down by a lot. Typically by, maybe by a factor of, for primary isotope effect, factor 3 or 4, significant. And so, since this is the rate-limiting step, metabolism is slower. If the drug is not metabolized as fast, then it's not being excreted as fast. It means you can use less of it, and so you have a lower dose. Now, it turns out there's a company that started up a few years back in Massachusetts that has gotten patents on a lot of drugs just that are deuterium substituted. And so, I guess they're making money that way too. One thing you should notice is that this particular drug has a structure that is common to an awful lot of compounds that are CNS active, central nervous system active. And I'll draw it here just so you can see it. It's this structure here. Okay? So that structure, that phenethylamine, that is common to a whole bunch of compounds that you're aware of. It's in morphine. And it's also in methamphetamine. Methamphetamine is this stuff. And so you can see it's got this phenyl, CH, carbon, nitrogen. Let's see, what's another one? This is ecstasy. So this also has the same arrow. It's not phenyl, but it's substituted phenyl, carbon, nitrogen. So that's a motif, a structural motif that recurs in CNS active compounds. That tells you something. That tells you something that all of these drugs are reacting with the same class of receptors. And so they fit into a protein site pretty much the same way. course, the effect is different for each one of them, but that's again something that is not surprising given the differences in structure. Okay, so now let's talk about something a little bit different. Now for something completely different for you, Monty Python fans. Okay, so terpenes in the isoprene rule. So what are terpenes? Well, you'll find out in a minute. What's the isoprene rule? Well, the isoprene rule tells you how terpenes assemble themselves into molecules, or how terpenes are assembled from isoprene units. So it turns out that there are a whole bunch of plant-derived compounds that some of which you know because you've smelled them or you've tasted them, that have structures that are multiples of 5 carbons. Okay, so they have either 10 carbon atoms, 15, 20. There are a few with 25, some with 30. And these have names. They're called monoterpenes if they have C10. Sesqui, which means one and a half, sesquiterpenes. Diterpenes, 20. 25 are called sesterterpenes, and then C30 triterpenes, and so on. Now, so this is something that people noticed way back when, that there seemed to be some kind of a ratio of 5, 5 times 2, 5 times 3, 5 times 1, and so on. And so the conclusion that you draw when you see something like that is that, you have all these molecules, they seem to be formed by, they have carbon atoms that are multiples of 5. That suggests very strongly that there's a 5-carbon building block that's common to all of them. And so if I take 2 of those building blocks, I end up with C10. If I take 3 building blocks, C15, and so on. And so the building block turns out to be this one here. And I've numbered this 1, 2, 3, and then the 2 fluorocarbons are kind of branched off. And remember we talked about isoprene as being a conjugated diene. So these compounds are called isoprenoids. Now, isoprene is not the building block, okay? So the building block isn't isoprene, but you can kind of see an isoprene unit in all of these terpenes. So let's take a look at some of these and see. Okay, so geraniol, this is a very simple terpene, and it has a C10 structure. Geraniol is responsible for the rather pleasant odor you get. If you get a geranium plant, you kind of crush the leaves and smell. That's what you're smelling. You're smelling geraniol. And I think you can see here that you've got 2 terpene units. So you've got these 5 carbon atoms here, and if you kind of close your eyes and look, that looks like 1 terpene unit. Close your eyes and look at the other one. Looks like you've got another one. 1, 2, 3, 4, 5. This one, of course, is oxidized, but this is pretty clearly formed by 2 terpene units that have been joined up one after another. If we call this carbon atom 1, 2, 3, and these are 4, then to distinguish this would be 1 prime, 2 prime, 3 prime, 4 prime. So this would be called a 1 prime 4 junction of the 2 units. You don't need to remember that, but there is a nomenclature to tell you how the terpene units fit together. Okay, so the isoprene rule just says that you have a multiple of 5 carbon atoms in your structure, and the carbon connectivity is consistent with this piece hooking up to that one. So let's take a look at some examples. And I guess what I'll do is I'll cover up the side of the page a little bit. Okay, so here are 2 terpenes. Very complicated ones. This one is clove oil. So if you bought, clove oil was used as a topical, I think it still is used as a topical anesthetic in dentistry. So very often before they put that little needle into your gum to numb your tooth, they swab the gum with clove oil. That kind of numbs it a little bit more, and then the needle doesn't sting. So that's this stuff here called caryophyllene. Now, another terpene is this one. This is a little more sinister. This is a fungal plant toxin. This is called Helminthosporal. Notice that Here you don't really have any functionality except for these alkenes. Here you have an aldehyde and an aldehyde. You still have a double bond. So this kind of tells you that there's a tremendous amount of variability in structure that you can derive from just hooking terpene units or isoprene units together. So even though the building block is trivially simple, and 5 carbon atoms, how much simpler can you get? You know, by hooking these things up together in various ways, you can end up building a lot of complexity. So now let's take a look and see, you know, are these in fact terpenes? In other words, do they certainly satisfy the first rule, multiple of 5 carbon atoms, but is the carbon connectivity consistent? It turns out it is, but you have to look at it fairly carefully. So I've color-coded these terpene units for caryophyllene. You can do this on your own if you want, but here's one terpene unit, here's another, and so on. This one, of course, doesn't have the expected connectivity because you have a gem dimethyl group here, but you certainly have 3 terpene units. And with helminthosporal, you still have 3 terpene units, 1, 2, 3, 4, 5, or 5 carbon pieces, and I've kind of drawn them out in a way that suggests the final structure. And so, yes, each one of these is a what? It's got 3 terpene units, so these are what? These are sesquiterpenes. So C15 compounds. And you'll notice how different the structures are, but they're all made from the same building block. So the question, of course, then becomes, well, gee, how are they assembled, and what are exactly the building blocks? Because you know the building blocks are not isoprene. Now we're going to talk about cholesterol separately, but that also is biosynthesized from terpenes. But let's take a look at terpene biosynthesis first. And so how does this work? Okay, so if I forget about the phosphorus here, if I just look at this piece, that's an isopentenyl alcohol. And the phosphorus piece, the diphosphate, this is called pyrophosphate. This is nature's leaving group. Okay, so nature doesn't use phosphonates, bromides, iodides, chlorides, it uses pyrophosphates. Now it's a very clever system because the pyrophosphate by itself is really not a very good leaving group, and it can't be. So imagine this. I mean, if you have a cell and it's going to do some chemistry with this pyrophosphate, you can't have something that is just indiscriminately reactive because you know it's going to if it has a strong good leaving group, then that reactivity is going to manifest itself whether there's an enzyme present or not. No good, because then you don't get selectivity. So if it's going to be useful for biosynthesis, then you have to be able to control the reactivity, and you want that good leaving group activity to be present only at the right time and the right place. Okay. Now, isopentenyl pyrophosphate is one of the building blocks, and you can notice that isomerization here gives the gamma-gamma dimethyl pyrophosphate, or DMAP. So IPP and DMAP are the two pieces that you have. And they differ only in the location of that double bond. Now the isomerization takes place again under enzymatic control. Now, in order to convert this into a good leaving group, you need a metal. And the metals that you use are typically magnesium +2, or sometimes manganese +2. These are both metals that are found in cells. And so what happens is that you have a divalent metal. It sees these 2 negatively charged oxygen atoms and forms kind of a chelate. And now this becomes a very good leaving group. And so this now can act as a leaving group, whereas this is not. Now that's important because if the magnesium is present only at the active site of the enzyme, then only at the active site of the enzyme are you going to do chemistry. And so the enzymes that do this are called prenyltransferases, and there's some bewildering variety of these. So how does it work? Well, the way it works is according to a mechanism that you guys have seen in Chem 272. And the mechanism is a cation reacting with an alkene. There were several problems at the end of one of the chapters that had you do exactly that kind of chemistry. And so if PP is pyrophosphate, and I'm assuming the metal is there. So if I ionize this, I end up with an allocation. It can get intercepted by the pi bond. That gives me that red CC bond and a cation right there. The cation right there, I'm drawing a little differently, loses a proton from this carbon atom, that's that carbon atom. And then you end up with the pyrophosphated geraniol. And that's the first step in the biosynthesis of all terpenes. Okay, that's the very first step. Now, once again, you look at this and say, you know, this doesn't make sense because we talked about something just like that not that long ago, and you showed something different. And I did. I showed not a pyrophosphate, but a chloride ionizing to give this resonance stabilized cation. That gets intercepted not by an alkene, but by water. And look at this. We end up with most of the product taking place at the tertiary carbon and only a little bit at the primary carbon. But here, I'm not showing any kind of reaction at the tertiary carbon. I'm showing all the reaction taking place at the primary carbon. So why is that? Did the rules change? No, the rules didn't change at all. What happens is that this is a reaction that's being done under enzymatic control. And so the proximity of this carbon atom, in other words, this carbon atom may only be able to reach here and not there because these two molecules are being constrained within the enzyme's active site. And so don't expect for enzymatic reaction to see the same kind of regiochemistry that you see for non-enzymatic reaction. So geranyl pyrophosphate leads to all of the other compounds through repetitions of this reaction. Now, you can say that, well, okay, but you know, this doesn't look right either, because if we're just repeating this reaction, then all we're doing is forming a linear species. And you're right, but you should also recognize that there's other reactivity that's available to this pyrophosphate. In other words, I could imagine this pyrophosphate now ionizing and the cation being intercepted by that alkene. And that is also a step that takes place. I urge you to look into how that might happen. Okay? Okay, so now let's talk about steroid biosynthesis. This turns into, this is probably one of the best examples, you know, of how organic chemistry is essential for understanding biochemistry. So this is farnesyl pyrophosphate. Where did farnesyl pyrophosphate come from? Well, it came from geranyl pyrophosphate, the one that you saw on the preceding slide, with one more isoprene unit. So I combine now 3 isoprene units, and now I have the trimer, the trimeric species, C15, farnesyl pyrophosphate. Now it turns out that there's an enzymatic reductive process that takes place, where you get 2 of these farnesyl pyrophosphates, and you join them head to head here, that red bond. So this now C30 compound, because this is 15, so 2 15s is a C30. This is called squalene. How many of you are biologists? Lots. What does the name squalene remind you of? Come again? I think we fishermen. Where did we fish on the East Coast? No, okay. So on the East Coast, Northeast Coast in particular, you'll be fishing one day and catching lots of fish, and all of a sudden, nothing. And the problem is that you have a species there called Squalus dogfish. And they show up and they end up eating the fish off your line and chasing everything away. So squalene comes from Squalus acanthius because it's isolated inter alia from shark liver oil. So that's where the squalene word comes from. Now, squalene is, it's just a polyene, and it undergoes a very specific epoxidation to give you a single enantiomer of that epoxide that I've shown. Now, the epoxide is formed only at one site, not at any of the others, only at one site. And it gives you one asymmetric carbon. This carbon is not asymmetric because you have two methyl groups there, right? So this is 2,3-oxidosqualene. And then the most remarkable reaction is there's another enzyme that comes in. So this floats around, goes into an enzyme active site, and lanosterol comes out. And so you go from this very simple linear molecule to something that's got 4 rings and 7 asymmetric centers all in one step. That, to me, is, it seems almost magical. I mean, how does that happen, for heaven's sakes? Okay, so first let's take a look at how the epoxidation takes place. Now, when we talked about epoxidizing alkenes way back when in Chem 272, what was the reagent that we used? We used MCPBA, metachloroperbenzoic acid, right? And so that was a peroxide, a peroxy acid. Turns out nature uses something that's not quite the same, but very similar. It uses, and I've not shown the entire structure here, this is the business end, but it uses this peroxy compound. So this is the reagent, so to speak, that reacts at the enzyme active site to give you this epoxide. So the epoxidation is remarkable. The whole process is remarkable, but really this is what we want to take a look at. How the heck does that happen? Well, okay, so we know epoxides have what? They have strain, right? And you also know that epoxides have a basic oxygen atom. So if I allow an epoxide to react either with a Lewis or a Bronsted acid, I end up getting a proton transfer reaction in case of Bronsted acid, and I form a protonated epoxide. Now, just as we saw in Chem 272, reactions can take place. You can think of this bond, this one here breaking, to form a cation where my pen is, and then this pi bond reacting with that cation, that generates another cation. There's another pi bond that reacts with that. That generates another cation. We form these two red sigma bonds, and it goes on like that. Now, this is what would have happened if the process were stepwise. Now, your book says that this process, to go from oxidosqualene to lanosterol, is concerted. And in fact, that's the old way of, that's been superseded in recent years. The evidence for concertedness is that it is stereospecific. That's supporting evidence. That doesn't prove it. The other evidence that has been given for concerted reaction is that if it were stepwise, you would form cations. Those cations would have a lifetime. They would lose a proton, they add a proton. So you form cations reversibly. So they ran the enzymatic reaction not in H2O, but in D2O. And they didn't see deuterium incorporation. So I said, aha, that means that there can be no reversible formation of cations. That also is not particularly convincing evidence, but let's take a look at this. Okay, so the process is supposed to be taking place in one step. So here it is all run together. Now, I've shown oxidosqualene in the reactive conformation. Okay, now you should recognize that this is kind of cheating, because if you have a molecule like this, it's got a sigma bond here, sigma bond there, sigma bond, sigma, 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 all these sigma bonds. All the sigma bonds have rotational freedom, don't they? And so the numbers of conformations that are available to a molecule with that complexity is astronomical. And there's only one of them that's going to react to give you inositol. And so why is it then that the reaction works as well as it does? Well, one reason is because it takes place at the active site of an enzyme, and the enzyme constrains this molecule to be in the active conformation. So again, you have a cation forming here at the same time as you're forming this red bond. Then you have to form a bond here, then a bond there, and so on. And now, if I complete that process, I will make all the red bonds that you saw, all these sigma bonds. Now, this tells you also a few things. It tells you that the whole process is downhill energetically, right? Because what you're doing is you're exchanging how many? Five pi bonds for 5 sigma bonds. And you know the sigma bonds are a heck of a lot stronger than pi bonds, and so energetically this is going in the right direction. Because of the symmetrical nature of this, the fact that you have a methyl group here, this D ring, these are A, B, C, D rings. The D ring is constrained to be a boat. Now you know that boat conformations for 600 rings are higher in energy than chair. And so that provides you with a chemical driving force for the next step, which is even more amazing. It is a concerted migration of this hydride to that cation, followed by this hydride to the cation there, and so on. So remember what cations can do. They can undergo rearrangements. So here's a rearrangement of a cation. How do cations rearrange? Typically by either an alkyl migration, a 1,2 alkyl migration, or a hydride migration. Here it's a hydride that gets the process going. So hydride moves from this carbon to that one. That leaves me with a positive charge there. This hydride moves over. That leaves a positive charge there. This methyl moves over. That leaves a positive charge here. And then that methyl to generate this cation. In the last step, you lose a proton, and that gives you inositol. Now, each one of those migrations takes place superficially. What does that mean? Well, it means that it takes place from the same face of the incipient pi bond. So in other words, you don't have a hydride going to the other side of the pi bond. It goes from the same side, and that's why the stereochemistry doesn't get one of the reasons why stereochemistry doesn't get scrambled. And so this process is just not any different from the cation rearrangements that we talked about in Chem 272. It's just there's 4 of them strung together. Okay, now this all seems a little bit too tidy. And so let's take a look at what I said. I said that, conservative, I'm not so sure. When we first talked about cations, there's something we talked about, stability, right? There was a rule, what was it called? Yeah, there's a rule that we talked about when we talked about alkene substitution chemistry that took place through cations that told you which radioisomer of the product you would get. It's called Markovnikov's rule, right? And so you learned that tertiary cations are more stable than secondary, more stable than primary, and so on. And so, so now let's take a look here. Okay, so let's look at the first step. Okay, so I form a, I start to form a cation here, and I form the first bond. That gives me what kind of a cation? Tertiary, right. I form the second bond. What kind of cations does that give me? Tertiary. Okay, so first bond gives me tertiary right there. Second bond gives me tertiary right here. What bond is the third? What kind of cation does the third bond give me? Secondary. Okay, so that all of a sudden doesn't make complete sense, right? And so actually, it doesn't seem that, it seems as if you form the first two rings just fine. And then it looks as if you actually get Markovnikov's rule product, but that then rearranges to give you the Lonostrol that you get in the last step. Now, how do people puzzle this stuff out? How do you suppose people figure out how these enzymes work? Here's how they do it. They do it through a lot of synthetic chemistry. So instead of making synthetically in the lab, not using enzymes, instead of making this substrate, you make something that differs in this area. And in fact, it differs in a way that prevents it or enables it to do certain kinds of chemistry. You feed that to the enzyme, you fish out what product you get, and from that you can infer what the enzyme is doing. It's laborious and painstaking, but it actually gives you a lot of information. And so it looks as if this reaction is not exactly concerted, but that's maybe a point for a different class. Okay, so this wraps up chapter 17 on allylic and benzylic reactivity. I'll go over the chapter just briefly in the time remaining. We learned that there's a kind of high reactivity associated with benzylic or allylic positions, and that is not at all surprising given the fact that whether the reaction proceeds through a radical or a cation or an anion, even if there's an SN2 reaction taking place, that the presence of that adjacent pi system can stabilize the transition state. And so you can either stabilize the intermediate or the transition state by a pi overlap. Now, allylic hydrogens are these. If it's over here, it's non-allylic. This would be a benzylic hydrogen, and so on. And then this gets us back to drawing resonance structures. Now, there's a fundamental difference between benzylic and allylic cations, radicals and anions, and that is the following, that both of these carbon atoms in the allylic cation are reactive. But in fact, only this carbon atom, the benzylic cation, is reactive. No nucleophilic addition takes place in the ring. And the reason for that, as you know, is because were it to take place in the ring, we would lose aromatic stabilization. And so the transition state for that kind of a process would be much higher in energy. And so that's why it doesn't take place. On the other hand, as we showed moments ago, if you have an unsymmetrical allylic radical, then you can expect reactions to take place at both ends. And in this case, the ratio of products reflects the difference in stability of the two cations. On the other hand, for the benzylic case, only one product, never products where you've lost aromatic stabilization. Halogenation reactions are usually the first ones we talk about, and so for benzylic bromination, it's just a radical chain mechanism of the same type that we've seen so many times before. It's just that the hydrogen atom abstraction takes place with great selectivity at the benzylic position, because this is the weakest sigma bond. It gives you a tertiary benzylic radical. Tertiary benzylic radical reacts with bromine, and you get your bromine back, and you have your chain mechanism. Now, so this is the easy case. The case with allylic halogenation is complicated because you can get dibromination of alkenes without any kind of catalyst. For the aromatic case, we didn't have to worry about ring bromination because there's no ferric bromide or aluminum bromide or any kind of strong Lewis acid catalyst, so no issue of brominating the ring. But with the alkene, you don't need a catalyst, and so if I just mix these two together, that's what I'm going to get. Now, it turns out that I can favor the radical process in a couple of ways. The radical process is faster than this one, but this one can compete. And it competes very well by the reaction of polar solvent, because the intermediate bromonium ion is charged. So if I want to get this product, I don't use a polar solvent. And for reasons that we discussed, it helps to add the bromine much more slowly. So you have a low concentration of bromine throughout. That favors the radical process. The way you do that very nicely is using not Br2, but NBS, N-bromosuccinimide, as your source of bromine. The mechanism for this was another chain reaction, but one of the steps in the chain process was an ionic step. So the initiation process, again, not too surprising. You end up with a hydrogen atom abstraction, but then the ionic step is the HBr that you formed here, reacting with more NBS to give you a small amount of bromine. And so the amount of bromine is never very large in this reaction, and therefore you don't get the dibromination of the alkene through the ionic process. So then we talked about allylic Grignard reagents, and we said that these have the reactivity of allylic carbanions. They are reactive at both ends of the allylic system, but that is not to be taken as a resonance structure, but as an equilibrium, because remember this carbanion, it's not a free carbanion, there's a bond between the magnesium and that carbon, but it rearranges. So this is an allylic rearrangement, and whenever you have an allylic cation, anion, radical, always expect reactivity at both ends. The E2 eliminations are faster for systems like this, where the proton being lost is benzylic or allylic. And so even though I'm not forming a cation, an anion, or a radical, the reactivity is still higher for that hydrogen. And the reason for that is because in the transition state, I am partially breaking that carbon-hydrogen bond, and I'm partially forming a pi bond. That partially formed pi bond can overlap with the ring. That lowers the transition state for the loss of this proton versus one that is non-benzylic or non-allylic. And so now we know another way to accelerate an E2 reaction, and that is have an acidic beta hydrogen. So that will make the elimination reaction go fast. SN2 reactions are also much, much faster at benzylic or allylic sites than non-allylic or non-benzylic. And that, again, is something you can predict based on the structure of the transition state, which allows partial overlap of the developing allylic or benzylic system with your incoming nucleophile. So the bottom line is that you end up with a transition state that looks very much like an allylic anion or cation, and so that will lead to an increase in reaction rate. Oxidations can be done selectively at allylic or benzylic positions if one uses the right oxidant, which is manganese dioxide. You can form manganese dioxide, as I said, through this disproportionation reaction. The mechanism, which you should pay some attention to, is it's a radical mechanism, but of a slightly different type than we've seen. You end up forming a manganate ester that then does a intramolecular homolytic cleavage of a carbon-hydrogen bond, generating a diradical, which then collapses to the aldehyde in the manganese +2. A slightly different kind of oxidation takes place with either very hot or very manganese or potassium permanganate or very hot chromium trioxide, and that is this oxidative cleavage of alkyl groups from benzene rings. And that brings us to today's lecture, where we talked about cytochromes and terpene biosynthesis. So the last thing I wanted to say today was, for those of you who walked in late, chapters 12, 13, 16, and the first part of 17 should be there.